Welcome to ThirdEye Labs, where we make the unseen seen. This is the Exponentials and Logarithms lab. The concept episode showed why logs matter. Today we put them to work on a real digit classifier and walk 3 use cases you hit in real machine learning: a loss curve that hides a straight line, a softmax that quietly overflows, and a confidence score that knows when it does not know. Before we dive in, here is what you need. You should have watched the Exponentials and Logarithms episode, and you need a little NumPy. We use one built-in dataset, the handwritten digits, so there is nothing to download. Everything runs on a laptop in seconds. Section 1. Recap. The episode gave us 3 facts. Exponential growth outruns linear growth because it grows in proportion to its own size. The logarithm is its inverse; it asks how many doublings. And its superpower, the log of a product equals the sum of the logs. We check all 3 in a couple of lines of code. Section 2. Build the tools. 3 little functions power everything that follows. Softmax turns raw scores into a share of the vote, probabilities that add to 1. Log-Softmax computes that in a stable way using the Log-Sum-Exp trick, and Cross-Entropy adds up the surprise of each prediction. That is the log likelihood we train on. Section 3. Train on digits. 1 real dataset, the built-in handwritten digits, and 1 tiny model softmax regression. We run plain gradient descent for 300 steps and record the loss at every step. The loss starts at the natural log of 10, a pure random guess, and ends near 0, with about 97% accuracy on held-out digits. Section 4. Use case 1. A log scale reveals hidden structure. On a linear axis, the loss looks like a cliff and then nothing. You cannot see the late progress at all. But put both axes on a log scale, and a straight line appears. The loss is following a power law. Loss shrinks like step to the -1/2. This is the same shape as the scaling laws that govern how the largest models improve with more compute. The log scale is a zoomed-out map that fits the whole story on 1 page. Section 5. Validate. Our hand-built pieces have to match the trusted libraries. Our softmax and Log-Softmax match SciPy to 12 decimal places, and our cross-entropy matches Scikit-Learn's log loss exactly. The tools are correct. Section 6. Use case 2. Break it, then fix it. Once a model is confident, its scores get large, and that is where the naive softmax dies. It calls the exponential first, and the exponential of 1000 overflows to infinity, so infinity over infinity is not a number, and training collapses. The fix is the Log-Sum-Exp trick. Subtract the largest score before the exponential. It is like measuring everyone's height relative to the tallest person. The answer is identical, but nothing ever blows up. Section 7. Use case 3. Confidence and the unknown. The top softmax probability is not just a label, it is a confidence score. On real digits, it sits near 1. But feed the model pure noise, something it has never seen, and that confidence collapses. Used as an out-of-distribution detector, confidence separates digits from noise with an area under the curve of 0.93. Reject anything the model is unsure about, and we catch more than half the noise while wrongly rejecting only 5% of real digits. It is like a spam filter's certainty, not just its yes or no. Let us recap what we did. We built Softmax, Log-Sum-Exp, and Cross-Entropy by hand and checked them against SciPy and Scikit-Learn. We trained a digit classifier and saw its loss become a straight line on a log-log axis, a power law. We made the softmax overflow safe with the subtract the max trick, and we turned its confidence into a detector for inputs it has never seen. The big lesson: logarithms are not abstract. They are the everyday tooling of machine learning. That is it for this lab. Please like and subscribe ThirdEye Labs if you enjoyed it, and tell me which use case surprised you most. The full code is in the description.